Hello everyone and welcome back. Let's continue on with the May-June 2023 series, paper number 2, variant 2 for physics AS level questions. Now before this we have completely solved all of questions 1, 2 and 3 so far, and they have been dealt with in separate videos that have been uploaded before already. So before we go further into question 4 in this session, do look at those questions, attempt them in your own time and then cross-check with our solutions before we go any further. So give those a watch first before we dive into question 4. So let's begin. Now here we have the following. A spring is suspended from a fixed point at one end. The spring is extended by a vertical force applied to the other end. The variation of the applied force F with the length L of the spring is shown in figure 4.1. Now before we go any further, two things must be pointed out. Number one is that on the x-axis we have centimeters, not the regular SI unit of meters. And secondly, where you would normally expect extension to be on any one of the axes, you instead have something like length. So these are just two things we'll just highlight first and foremost, and now we'll go ahead. So A says that for the spring, state the name of the law that gives the relationship between the force and the extension. We know that there's only one law that states that the force applied to a spring is directly proportional to its extension, and that is what we call Hooke's law. Next we have part B, determine the spring constant in newtons per meter. There's only one piece of information that we can use here, and that's this graph figure 4.1. And we can in fact bring back the law that I wrote in the second slide, that is force is directly proportional to extension. And from here we have the formula itself that illustrates Hooke's law, which states that the force applied is the spring constant times extension. Now if I were to make the spring constant the subject of the formula, I'd have force over the extension. Now you can clearly see how if we look at the axes over here, you have force on the y-axis, and then now here we have length on the x-axis. But if you were to take a change in length, that would merely be what we would call extension. So force over extension is pretty synonymous to basically seeing how a quantity along the y-axis is changing with respect to the quantity on the x-axis. And so the spring constant is nothing but the gradient in this scenario, right? So we effectively have to calculate the gradient of this graph. Now we can take the extreme edges to make it easier for us. We'll pick this point and then we'll pick this point. So let's label the points that we have. On this point, this first point I label it A and the second point I label it B. And let me in fact write them over here. For point A we have a length of 8 centimeters. And I'll be sure to write it in meters. That would be a division by 100 and we should get 0.08 meters, right? And at point B, the length that we have is 24 centimeters, which is the same as 0.24 meters, right? Next, we want to also look at the corresponding forces. Now, for point A, the force that's exerted is 0 newtons. And for point B, the force exerted is a total of 12 newtons, right? So we know that the spring constant in our case is the gradient, which would be a change along the y-axis, which is 12 minus 0, divided by a change along the x-axis, which would be 0.24 minus 0.08. So now it's just a matter of plugging everything into your calculator and let's see what do we get. So 12 divided by 0.24, then minus 0.08. Let's see what do we get. We get exactly 75. And here, because all of our units are already in newtons and meters, everything's in standard units, our final answer will be 75 newtons per meter, right? Quite straightforward. Now let's look at part B, or rather Now that we're done with part B, let's look at part C now. C says determine the elastic potential energy when F is 6 newtons. Now this is where they've given us the specific value of force, which is 6 newtons. And we want to determine what's the elastic potential energy at a force of 6 newtons. Now this is where we can take one of two routes really. We could either just use the spring constant we've already found out and then just figure out what extension there is. That would actually be a lot more straightforward. Another approach would be to take the area underneath the graph, but in effect it's really the same approach. So it would be easier to use the value that we've already calculated for the spring constant, that's 75 newtons per meter. They've given us the force at which we want to evaluate the elastic potential energy, and that force is 6 newtons. We can use our graph to figure out that at 6 newtons, how much length has the spring encountered, and that is a length of 16 centimeters. So I'll write it down here that at a force of 6 newtons, the length L of the spring is 16 centimeter, or we could definitely convert this to meters as 0.16 meters. Now the thing here is that when you want to calculate the elastic potential energy, the formula we use is half times k times x squared, where the x is extension. We can't really use 0.16 meters here because that's the length, not the extension. But what we can do is calculate the extension separately. The extension would be the new length L that I've already written out here minus the original length. The original length being the length of the spring when there is no force attached to it. So if we look back at our graph, when the force is 0, the length that the spring has is 8 centimeters. So the original length L naught, let me write it here, is 8 centimeters, which I can write as 0.08 meters. So the extension at a force of 6 newtons would be 0.16 minus 0.08 meters, and that is equal to 0.08 meters. So now that I have my extension and my spring constant, now I can easily evaluate elastic potential energy. Half times 75 times 0.08 whole squared, and plugging everything in, your answer should be approximately 0.24 joules, right? So this was all related to Hooke's law. I hope that through this question you were able to revise some basic concepts of the entire chapter of deformation and how it pertains to springs and its Hooke's law. And moreover, we hope that you were able to understand our solution. Next time we'll dive into question 5. So stay tuned for that. Thank you.